This next group was determined to study a nebula, and I begged them not to. And I have never studied a nebula myself before. I asked if they could at least find a variable star in the nebula, which they did. They scoured catalogs. They found a variable star, and I was like, "Oh, okay, I can watch things get brighter and dimmer. I can do that." Well, this turned out to be, again, more complicated than we bargained for, and I will let them tell the story of this crazy pulsating star that they found inside NGC 1501.
Right, so hi everyone. In our study, we investigated the periodicities of the variable star known as CH. So previous research papers have found that CH-CAM has not one pulsation, but many. So because of that, our research goal was to try to confirm these periods, as well as potentially identify new periods. And you can see on the right of this slide an image of CH-CAM that we composited. Yes. So why does this matter? Well, CH-CAM is the central star of the nebula NGC 1501. And currently, CH-CAM is in a stage of stellar evolution where it has not yet fully cooled off from going nova, but has not yet reached the white dwarf stage, so it's a pre-white dwarf right now. And other stars of this type that are at the same stage typically have periods ranging from around 30 seconds to 25 minutes, sometimes longer. And of note is that the amplitudes of these periods are typically very small, ranging from 1,000 to 0.2 of a magnitude. So understanding this star's periodicities will help to further our understanding of stellar evolution between this quick phase between nova and white dwarf, and also help our understanding of nebula formation. And of note is that there has already been a study that has used the change in periodicities of stars just like CH-CAM to provide an estimation of the age of the galactic disk.
All right, so we took images over seven different nights, consecutive imaging. And with these images, we used 3 different methods of analysis. One using aperture photometry on Image J, another using source extractor photometry, and another using PSX photometry, although we have not finished that analysis, so we will not be showing that data today. So we used these different methods to try to account for the peripheral light from the nebula, and also to try to show the small pulsations of the star. Next slide, please. Okay, so here are 2 periodograms from our analysis. On the left from Image J, and on the right from source extractor. As you can see, or maybe not, they have different magnitudes, and also are with different lengths of period. So Image J, we only found data above 80 minutes for each period, and with source extractor, we've only found periods that are less than 80 minutes, so we're still looking into that. And again, we are also looking into PSX to confirm our findings.
Next slide. So this is one of the graphs from the source extractor method, and it's been folded around a value of around 24.7 minutes. And as you can see from the y-axis, the variation in magnitude is rather small. Just from the mean to the peak, it might be around 0.1 units of magnitude. Then so using these small amplitudes in addition to the very messy data from the extra light from the nebula has made it rather difficult to find all the periods in the data. And then after finding these periods, for calculating the amplitude, We then use a correction based on the exposure time of the images to then more accurately calculate these amplitudes. This, in some cases, made a 20% chance, a 20% change, I believe, in the amplitude that we found. And this 24.7 minute period most likely corresponds to one of the many periods that have been found in the literature from ranging around 23.8 to 25.2. This is one of the graphs from the Aisha imaging method. And as you can see, a sine curve has been fitted to this data. And it has from the peak to the valley, it has about a amplitude of 0.062 units. Due to the very long periods with respect to exposure time, the correction that was used for some of the source extractor periods was not used because it ended up being a negligible correction. This period right here most likely corresponds to one of the periods found in the literature, which is around 87 minutes. So, after analyzing the different periodograms from each method, we have found up to around 20 different periods, although some that were close in value were then grouped, and so this ranges from around a little over 10 periods. And these have amplitudes from around 0.01 to, in some cases, even above 0.1 to 0.19. And these also had periods ranging from 7 to around 111. Many of these periods, not all, aligned with the literature found in the periods in the literature, which was the legitimacy of many of the periods found by this study. And the new periods, because of the short phase in solar evolution in which our star is in, most likely are also legitimate. But this is, again, still being studied.
We have a question online.
The question from Thomas Smith is, I didn't hear this mentioned. Did you use the same photometric annulus for both source extractor and outgoing?
As in the same radius?
Same photometric annulus.
Yeah. Yeah, the same. Yeah, it was the same size. 6 units. Yeah.
How big is that compared with the nebula?
It was just around the edge of the blurring of the star, so it would say it's like, I think it's like a sixth of the nebula's width.
Trying to capture the star.
Yeah, just the star,
exclude
not the
nebula. And then the sky annulus, the donut.
I'm pretty sure I remember it being 11 units. That surrounded the periphery of the nebula.
Trying to exclude the
Yes.
nebular light.
If you look at the way source extractor works and the way astral image J works, source extractor uses more of a PSF or point split function measure. And in fact, and that's why I suspect it shows many of the shorter periods because it's a better fit to the parent star. And you might consider using something like DAO that uses point spread mechanisms to measure your star. But particularly the graph you showed with the 89-minute period clearly has a much higher embedded frequency, which you can almost read on the chart. And astral image J isn't doing a job for you.
Okay, thank you for the recommendation.
That looks like real data to me in the Wiggles. Yeah, and which is, one of those 7. What was your exposure time on that one?
2.5.
Yeah, there's your 7.
Another technique that you might consider is something called date compensated digital Fourier transform. This is something that AVSO came up with many years ago, the gaps in the data, if there are any gaps, nightly gaps, which we almost always have, they alias and mess up most standard Fourier transforms. So Grant Foster was the author of that, and that's available in B-Star software from AVSO. So they compensated Fourier transform might resolve what you're seeing here.
Yeah, okay, the one that we used was a tool for Skynet, and it used non-sparkle, so I don't know the details of that, but I think that is a really cool one to check out. So.
Yeah. Ranzo or both have DCDFT. So it's worth trying.
All right.
So what was the telescope system that you used to get the data?
We used the Las Cumbres Observatory Network, so that took data from, I think it was one in Texas.
There was one in Texas, one in Hawaii, one in Chile.
How big are they?
Yeah, 0.4 meters.
Wow. 0.4.
0.4.
Okay. You say, I ought to sign up for this. Oh, yes, filters.
Use a blue filter.
Okay.
Does it correspond to the same filter?
V as
Sorry.
in Victor. Yes.
How hard was it to get scheduled time on the scope like that at an observatory?
So we took the images over 7 different nights, and I think we had originally 10 requests, and 3 of them got canceled. So that's why we had only 7 nights. But on those, it wasn't difficult to get the schedules.
Does anybody in the room know or have an opinion on a star like this that has a huge number of periods? Does pre-lightning help? I'll take that as a no. Okay, I gotta invite. Find the most prominent period, do a phased light curve, subtract that, and then rerun the DCT. Did the question make sense? You can see how you're going to find that one period, subtract it from the data, and then rerun. It might help narrow down what the most prominent periods are.
The other thing that you've got going here is what you have is real interesting data on stellar size knowledge. Because what's going on is this is collapsing into a white dwarf. You're looking at these different modes of propagation through the star, and combination of Gaia data with the apparent magnitude and some other stuff. You'll be able to actually figure out the velocities, the diameter of the star that you're working on, and that will help you sort out what modes you're looking at. You're doing a lot of diagrams.
Do you happen to remember the magnitude of the star was what, about magnitude 13? Is that too faint for tests? Magnitude 13, 14. Okay, so that might, homework assignment, might be interesting, is go to the astronomical something, and find test, TESS data, and see if they've got photometry on the star. If they do, you might be able to get 2-minute observing cadence continuously for a month with supremely accurate photometry. Oh yeah, minutes. Yeah, there may be something in it. This will be a long shot. Okay? Thank you very much.
Thank you.